Okay, hello everyone. My name is Ahmed Shokry. I'm delighted to present our paper, A Quantum Algorithm for RF-based Fingerprinting Localization Systems. The paper is co-authored by my advisor, Professor Mustafa Youssef from EUC and Alexandria University, Egypt. So the current state of location tracking systems is that GPS doesn't work indoors. Propagation models do not provide a good accuracy, especially indoors, as they need a direct line of sight with access points in the environment. And finally, fingerprinting systems can provide high accuracy in both indoors and outdoors environments. So as you know, fingerprinting techniques work in two phases, offline phase and online phase. In the offline phase, we collect the set of received signal strength measurements from different access points in the environment at different ground truth known location to construct the fingerprint database. And then in the online phase, a user stands at unknown location, scanning receive signal strength from different access points. And then we match the online receive signal strength vector heard by the user with the ones stored at different fingerprint locations. And then the closest location in the signal space is reported as the estimated location. The problem in fingerprinting-based localization is that it does not scale to a worldwide scale. This, of course, because of the data storage space overhead and the matching processing overhead. So our contribution is that we enable scaling fingerprinting-based localization to a worldwide scale using quantum computing, which can provide an exponential saving in both space and running time of the classical fingerprinting compared to the classical fingerprinting-based localization. We evaluate our quantum algorithm in 3 real test beds that cover different scenarios indoor and outdoor using different technologies like Wi-Fi and cellular signal. And we implement our quantum algorithm on real IBM quantum computing. So quantum computing is a new field at the intersection of physics, mathematics, and computer science. It leverages the phenomena of quantum mechanics to improve efficiency of computations. Nowadays, several commercial and academic institutions claim the quantum supremacy, so one might expect that quantum computing would be the mainstream technology within years. The basic unit of information is the qubit. It's like the classical bit. Qubits can have various physical implementations like the polarization of photons or a spin of electrons. And the qubit, unlike classical bit, qubit can exist in a superposition of both 0 and 1 simultaneously. So for example, this is a state psi equal alpha 0 plus beta 1, where alpha and beta called probability amplitudes, and the state of qubit is normalized in a way that alpha squared plus beta squared equal 1. But when we try to measure a qubit, when we try to know its state, a qubit jumps to either 0 or 1. It jumps to 0 with probability alpha squared and jumps to 1 with probability beta squared, losing both alpha and beta. Operations on qubits are usually represented by gates similar to classical gates. Gates can be applied to a single qubit or a qubit register, which is a group of qubits, leading to changing the probability amplitudes, which is always referred to as interference. The first gate is the NOT gate. It converts 0 to 1 and 1 to 0 like classical NOT gate. However, it can work on a superpositioning state to convert alpha 0 plus beta 1 to beta 0 plus alpha 1. Second gate is the Hadamard gate, creates an equal superposition of both 0 and 1. So for example, if we input 0 to the Hadamard gate, it converts it to 1 over square root to 0 plus 1 over square root to 1. The control swap gate swaps the two target qubits psi and phi if and only if the source qubit, the first qubit, is 1. A quantum circuit is like classical circuit. It's a combination of quantum gates. Single line represents quantum information, while double lines represent classical information, and the gates acts on the input qubits to change the combined circuit state to reach to the desired state. And of course, one needs to perform the measurement operation to get the outcome of the circuit. So for example, this circuit outcome is 0 with probability half and 1 with probability half. So one need to be careful when designing quantum algorithms because the outcome is random. Okay, so our quantum localization algorithm is a fingerprinting-based localization. The input to our quantum localization is online receive signal strength vector heard by the user, and offline receive signal strength vectors at different locations in the fingerprint. The first phase is the quantum state preparation, where we encode the receive signal strength vectors to quantum particles. Then we use quantum fingerprinting matching circuit to get the estimated location. So the target of quantum state preparation is to encode the received signal strength vectors into quantum particles. So for example, if we have a vector alpha, beta, gamma, and eta, where we encode which represents the received signal strength coming from 4 different access points in the environment, the state preparation phase transforms this vector to or encoded this vector into quantum particles. So a quantum state, quantum register state would be alpha 00 plus beta 01 plus gamma 10 plus eta 11. Note the exponential saving as we encode a vector that has 4 values into just a quantum register that has 2 qubits. This, of course, this technique is called amplitude encoding. So the second step in our algorithm is quantum fingerprinting matching. So the input to our quantum circuit is a single qubit in state 1 called the ancilla qubit, and the online receive signal strength encoded in a quantum register psi, and the fingerprinting RSS vector quantum register phi that represents the receive signal strength at a single location in the fingerprint, in our fingerprint. So our target is to calculate the cosine similarity between psi and phi, the online RSS quantum register and the fingerprint RSS quantum register. Of course, one needs to apply the circuit for different locations in the fingerprint, then calculate the location with the highest cosine similarity as the estimated location. So this is the input to our circuit, 1 psi phi. Then we apply the first Hadamard gate, which transforms the input to 1 over square root to 0 psi phi minus 1 over square root to 1 psi phi. Then we apply the control swap gate, which exchanges the quantum states when the ancilla qubit equal 1. Then we apply the second Hadamard gate, which transforms the second the system state from this state to that state. Then we normalize the quantum state, and we know that the probability of getting 1 for the ancilla qubit is proportion with is a function in the required cosine similarity. So after running the circuit for k times and measuring the output of the ancilla qubit, we obtain the similarity as follows: 2 times number of ones for measuring the ancilla divided by number of trials k minus. Okay, we evaluate our quantum algorithm in 3 real test beds that cover different environments, indoor and outdoor, and using different technologies like Wi-Fi and cellular signal. And we use both IBM real machine, quantum machine, and quantum simulator in our experiments. This figure shows the real machine, which called IBM Quantum Santiago machine with 5 qubits. The figure shows the topology of different qubits. The vertex color represents the single qubit gate error, like Hadamard gate error, and the arc color represents the two qubit gates error, like control not gate, and the vertical line represents the measurement error. Okay, this figure shows the effect of number of shots algorithm iterations on the median localization error. The figure shows that increasing the number of iterations leads to a better localization accuracy till it saturates around 4096. Okay, this figure shows the CDF comparison for the quantum and the classical localization. The figure confirms that both quantum and the classical fingerprinting localization systems can have the same accuracy in practice. On the other hand, this figure shows a comparison in the running time complexity between the classical and the quantum algorithms. So using quantum parallelism, one can design an algorithm that run in order m log n instead of order nm for the traditional classical algorithms. This, of course, is an exponential saving in the number of reference points or access points in the environment. And this complexity can be further enhanced to order log nm by encoding all fingerprint locations in one circuit. Okay, we presented a quantum algorithm for fingerprinting matching systems, and our quantum algorithm can provide an exponential saving for both space and running time. We implemented the proposed quantum algorithm on physical IBM quantum machine, which is IBM Quantum Santiago machine, and evaluated it in 3 real test beds. And we also showed that it can be scaled to a larger test beds using quantum machine simulator, and the results confirm the advantages of the proposed quantum algorithm compared to its classical counterpart over the different test beds. This, of course, opens the door for new contributions in the field of quantum localizations, like quantum spatial sensors, quantum device-free localization, how to secure our localization algorithm using quantum computing, and quantum computing for other classical algorithms. Thank you.